Alright guys, so we're gonna continue. Yesterday we spent a little extra time on the stuff that was pretty challenging. Made a little headway and a little bit of growth. We're gonna go ahead and move on. This is our last part for this particular half of Unit 12. We're gonna be the title's actually not correct. I should say factoring, but anyway, what we're doing today is we're gonna be factoring. All right, so that's an old strategy that we're familiar with, but we're going to apply it to trigonometric expressions today. And once again, it serves the same purpose. It's for simplifying expressions, and later we'll see that it's actually used for solving equations as well. So this, you don't need to write this. It's on that big sheet that I printed out for you guys. But just kind of reviewing factoring strategies here, the difference of squares. Okay, if you have two perfect squares that are being subtracted, what you could do is you could take the square root of each of those perfect squares, write it twice, one with a plus, one with a minus. So, for example, both x squared and 4 are perfect squares, right? So what we can do is we could take the square root of each one of those. The square root of x squared is x, and the square root of 4 is 2. You're going to write it twice, one with a plus and a minus. So we're going to do that today with some trig expressions, actually, but that's the difference of squares. GCF. GCF is whenever you see two or more terms that have the same factor in common, like in this case, both the first and the second one have an A in there, right? So what we do is we write that common factor outside. Thank you. We write what they have in common outside of a set of parentheses, and then we divide both of these by the common factor to find out what's left on the inside. And so you'd be left with B plus C. It's the opposite of distribution. You know, when you're distributing, you multiply something in. In fact, GCF is where you're dividing something out. Last one is the trinomial, and everybody does that a little bit differently. But anytime you have three terms, you can do what a lot of teachers call it the box method or the area method, area model, or reverse foiling. I've heard it called that too, but there's a few different ways to do it. Okay. Why don't you guys try to do this really quick, see how you do it, Dad. I don't want to demonstrate because everybody does it a little bit differently. So you try to do what you can with it, and then we'll see if you guys got it right. Okay. And then you see how that happened? We're all good? Okay. Okay. That's a no? I thought maybe I saw a hand going up. Okay. Let's do it. So there's a few different ways. I've taught it with the area model myself. I put where did it go? Oh, I erased it. It was this, right?
Yeah.
Don't laugh at me. Don't laugh at me. All right. So the first term we put here, the last term we put here, the middle term we put in the middle. And what you do is you look for two things that multiply to make this x squared, right? So that would be x times x makes x squared, right? And then what makes 2? Well, that would be 2 and 1, right? Now we multiply to fill in our box 2x, and 1 times x gives me 1x. And here's the thing, when you're doing factoring, it's really just a guess and check thing. You can't really be sure it works or not until the very end. Here's how you can be sure it works. If these two numbers combine, these two combine to make the middle. So does 2x and 1x makes negative 3x? Well, almost. They make positive 3x, right? But I can fix that if I make them both negative, right? But the only way these can both be negative is if what else was negative to begin with? these guys, right? Notice that it's okay for both of these to be negative because they still make a positive 2 there, right? So there you go. So it's just kind of a guess and check process. Another way that I've seen this done is, and this is actually how I do it, but you just don't get to see all the steps sometimes in this process, but just go right to the answer, you know. What times what makes x squared, and what times what makes 2. And then you kind of just got to mess around with the signs and see what works. And if I made them both negative, that makes a positive 2, so that's a possibility. And then if you FOIL it out, you have to end up with that 3x in the middle. So that's another way you do it. In that case, it works. So anyway, so those are factoring strategies, but we're going to be applying them to trig functions today. So go ahead and write down example 1. Okay, so part of the skill here is not just the factoring, but it's also identifying which factoring strategy to use. So on number 1, what would you guys say this one is? Would you say that's like a difference of squares? Is that a GCF, or is that like the trinomial one we did? It's a difference of squares. So I'm going to label that now as is. And the second one, what does that look like? Yeah, they both have a sign in common, right? So that's a GCF problem, and this is obviously the trinomial one, because that's the last one to choose from, but also because, as you can see, there's 3 numbers there, right? So that's how you can tell. So once you know what they are, you know what strategy to employ. So let's go ahead and begin here with number 1. Cotangent squared minus sine squared. I find that sometimes it's just overwhelming to look at all these letters, right? So what you can do to simplify it for a minute is and you don't have to do this. In fact, I would encourage you not to if you don't need to. But what you can do is you could just take the first letter off of each one and make it like a slightly simpler thing to look at. So if I had c squared minus s squared and I did the difference of squares, what would I get? C minus S and? Yeah. But of course, that's not what you want to leave your answer as, right? Because we just use simple letters to make it easier. The real answer is cosine x minus sine x, right? And cosine x plus sine x. But like I said, if you don't need to do that, then don't. Just oh, it's not cosine. There's a downside to using the c, right? Is it cosine or cotangent? So make sure you don't make the same mistake I just did there. Thank you. Gotcha. All right, so
that says c minus s, right? Not divided.
Yeah, that was c minus. This is for you. All right. So let's how many of you guys feel like it's up to you? So we'll vote. So we could go the baby step strategy, or we could just do them all at once and let you guys try them all at once. So how many of you guys want me just to keep doing all 3 examples and move on, versus one at a time? So one at a time, people. You guys think you want to try one like that first?
Oh no, just do all 3.
You sure?
Yeah.
Okay. Okay, I'm down with that. If you are. All right, let's go ahead and take a look at the next one. Then we said this was a GCF, right? Did you guys write this one down yet?
Yeah.
Okay, so we'll go ahead and get started. So what do they have in common again? They have a sign in common. So we're going to put a sign on the outside, right? And we're going to divide both of these by sine. So what is sine x squared divided by sine x? So I'll be left with a sine x here. And what's sine x divided by sine x? 1. There you go. And once again, to make it look easier, you could rewrite this as s squared plus s, if that looks nicer to you and simpler.
Wait,
Sure, sure. So I think for me also what's helpful in understanding how to do this is just remembering it's the opposite of distribution. So, you know, if you were to take this sign here and multiply it in, that should take you back to where we were, right?
Yeah.
So what we did was the opposite. We divided out what they had in common. Okay? Are we still feeling good about doing all three? Okay. All right, let's go ahead and do number 3. Do we need to write that down? No? All right. So now this one in particular I think is really helpful when you're dealing with these trinomial ones. I think it's very helpful to go ahead and just write it with a single letter. So instead of tangent squared, I'm going to put t squared. Instead of 4 tangent, I'm just going to put 4t. It just is a lot more pleasant to look at. Okay? And so at this point, we would factor this. Okay? So if I were to factor that, I would get however you guys want to do it. But what you would get is t plus 2 and t plus 2. You get the same thing twice there. And so my real answer is going to be tangent x plus 2 times tangent x plus 2. So that's my real answer. And then I'll cross that off just so I know I'm not actually using it. Yeah.
What if you did the box method?
Oh, so you want to see the box method with it?
Yeah, can you?
Sure, absolutely. So once again, I would not do tangents, right? I would do t's, right? So what I would have in there is t squared, 4, and then 4t. And so what times what makes t squared? And what times what makes 4? Let's fill in our box. What would go here? And here? And do these make the middle? Yeah, so we're good. So it's t plus 2 and t plus 2. In other words, tangent x plus 2 and tangent x plus 2.
What happens to the x on 4t?
So that's a common question. So let me show you. Mean the t? Oh, are you talking about this thing here?
Yeah.
That's part of the tangent. See, this is tangent x squared, right?
Oh.
This. Remember how I write these like this?
Yeah.
This whole thing, I'm replacing that whole thing with t. So it's there. The x is there. I'm just, since the x is, it's a lot of, the way it looks is it looks like you're saying x times tangent, right? And especially since I was inconsistent here. You can put parentheses, but I don't usually do that. So it looks like I'm saying tangent times x, but I'm not. It's tangent with x plugged into tangent. That's like a function is what it is. All right. Any other questions about that one? All right. So here's some for you guys. The trick here is in identifying what strategy to use and then applying it after that. So go ahead and try them, see what you guys can do. All right, so Nathaniel, so we've already said that number 1 was difference of squares. So what did you get when you applied the difference of squares to this one?
Tangent x minus secant x and another tangent x minus secant x.
Close. The other one is plus. Yeah, so when you do difference of squares, one's plus and one's minus. All right, next one. Alyssa, this is also a difference of squares, so what did you get for that one?
Plus 1 plus 1, and then plus 1 plus 1.
Cool.
It would be great.
All right. We talked about how number 3 was a GCF, so Haley, what was our GCF on number 3? Cool. So I'm going to put that there. And then what I'm going to do is I'm going to divide that out of each of these terms. So what would that leave us with? Cool. Thank you. All right. And then we have number 4. That's the it's a trinomial, right? So Ale, what did you get when you factored that? Cool. And that's it, guys. So that's factoring. Now, that was just a skill building set, but our purpose for doing this is to do the same thing we've been doing for the past few days. And that is to, when you see these kinds of expressions inside of a trig expression, you have to be aware, oh, maybe I can factor that. Now you kind of end up with an interesting situation sometimes. Like when you look at this, honestly, that's really close to a Pythagorean identity. I don't know if you guys noticed that or not. So when you're doing problems, you have a choice to make. Do I do a Pythagorean identity here, or do I factor it? And so I'll try to keep them simple for you guys, and so it's not too confusing, but there it is. This one, by the way, is not quite the Pythagorean identity because it's backwards. But there's a way you could adjust it so that it fits. But we'll stay out of that territory for right now. Going back here, want to make sure you guys got this too, by the way. Be aware of the fact that a squared plus b squared, if you ever see a sum of squares, that doesn't factor. Okay? So be aware of that. It has to be a difference of squares. All right, the rest of our notes are in a separate set, so just a second. All right, so let's go ahead and put these things to work for us here. Go ahead and write down example 2. So for the examples I'm giving you today, we're not going to be I'm not going to be doing any of the first 3 strategies I taught you, where you have to change everything into sine and cosine, and also where you have to simplify complex fractions or get a common denominator. I'm not putting examples like that in there today. I mean, technically I could do that, but what I will be mixing a little bit in there is the main thing we're focusing on, by the way, is factoring. So every problem I'm going to give you is going to have a factoring strategy involved. But I think there's a couple that'll have a Pythagorean identity in there too to watch out for. So those ones are pretty straight to the point. So didn't want to overwhelm you with too much. So let's go ahead and do this one here. Now, one of these pieces of this expression is factorable. Which one is factorable? The one on the top. And what factoring strategy can we apply to that? That's right. And so if I do the difference of squares there, the square root of cosine squared x would just be cosine, right? And the square root of 4 is 2. One's a minus, one's a plus, right? And what can we do here? Let's reduce out. And so now I've got cosine x minus 2 equals cosine x minus 2. That was nice, right? Yeah. Yeah. Because it helps you simplify expressions and solve equations. So the next time you go to Walmart to buy a pair of pants, you can look at the length and be like, okay, sine squared. Just kidding. All right.
I wonder if some mathematicians really don't like that, their whole life is math to them.
It's nothing this insane, but I do make up problems. Like I remember one time. All right, so this is a student practice. There's actually a mistake here, though, before we begin. I'm going to rewrite it like this. Okay, that's supposed to be 1 over tangent x plus 1. So I'm going to let you guys go ahead and try that. So right here is our difference of squares, right, guys? And so if I do that, Alex, what will the bottom be?
Tan x minus 1 and then tan x plus 1.
Cool. All right, and then I'm going to ask Tia, what happens now? That's right. And now this one confuses people, but So when you cancel these out, right, this is a number in the denominator still, right? So you can't just say that equals tangent x plus 1, and that was my mistake. It's actually 1 over tangent x plus 1. And so they match. All right. Let's do another one. Go ahead and write down example 3 here. Down example 3. Here we go. So what factoring strategy do you guys think this is? GCF. Is that because I'm being boring and uncreative and every time I do difference of squares first followed by GCF? Or is that because you actually see it? Okay, good. All right. So it's a GCF because both terms have what in common? A cotangent of x, right? It might help if you kind of imagine there being some parentheses here, right? I don't know. Maybe, maybe not. There's a lot up there, right? So, anyway, that all aside. So I'm going to take out that cotangent of x. Now, if I take cotangent x out of that, what am I left with? And if I take cotangent out of this, what do I have? Okay. Now at this point, I'm just going to let you guys math it. So what do you think we can do here? Those go away, right? And so that leaves me with this. That's right. It's a Pythagorean identity, isn't it? We're good. Who said that? Was that Danielle?
No, it's like it's like proofs and compounds right after.
Okay. Yeah. I actually.
This, but I hate writing it out.
It's funny you say that. I actually was this close to doing that this way, but I didn't. Yes, proofs are always a challenge. All right, you guys try this one. Go for it. So I do have a mistake here. There's supposed to be a square on this sign. So as you were, sorry. Okay, so Anicio, what is my factoring strategy? Good. So we're going to take a GCF out of this, and what is the GCF there? Sine x. So I'm going to take my GCF and I'm going to put it here, and then I'll put a big set of parentheses after that. And what's going to go in the parentheses is what would be left if I divided it out of there. So, Brianna, if I divide sine x out of this, what would I have? 1. And then, Danielle, if I divided sine x out of this, what would I have left? Cool. And Sean, what can we do now? Cool. So that leaves me with this. And then Giselle, what's next? Okay, no problem. Let's try Armani, what's next? That's right, this is a Pythagorean identity. And what does it equal?
Sine x squared.
Good. So they match. And we're in business. Okay?
Yes, we're doing another example right here.
I'd like to. We only have 4 minutes, so for my last example, I'll just work through it just to kind of show it to you, but unfortunately, I won't get to practice it. We ran out of time.
Is it a different process?
It's just a different it's just a different factoring strategy. Why don't I give you guys this one to do instead, though? So go ahead and write that one down. I'm going to skip the other one because there's something that's a little bit extra in there that we don't have to worry about for now.
Okay.
You see that? All right, so what's a little bit different about this problem is that you're going to factor twice. What strategy would I apply there? The hard ones. The trinomials, right? And how about here? Difference of squares. So I'm going to do the bottom first because that's a little bit more straightforward. The top, though, got my X. All right, the top, I'll show my work over here. You don't have to write it like this if you don't want to. But we're going to factor sine squared plus 2 sine plus 1. S times S makes S squared. 1 times 1 makes 1. And then the two S's do combine to make 2S. And so I've factored it as sine of X plus 1 and sine of X plus 1. And then we can reduce out what they have in common. And they're the same. Okay, so that's all.